Hi. Thanks for coming. And it's rare that I have the opportunity to talk to such an audience, so I feel I'm excited and I feel really privileged to be here. So I'll talk about this joint work of mine with Marios, who you all know, and George, who some of you know. Marios is here in Ikoki, but George in the University of Pittsburgh, and he's a mathematical physicist. He works a lot with plane waves and various types of solutions in GR. So what I want to do today is I want to discuss about observables, but from my point of view. And I came quite late to the party, so there's a lot of things that I do not know about observables, especially how they relate to various programs of physics. But OK, since it's my point of view, maybe I should discuss a little bit first where I come from and what I do. I'm a logician, and I work in descriptive set theory. So what is descriptive set theory? Right? If descriptive set theory is a theory, a complexity theory. If descriptive set theory cared about the finite, it would have been computational complexity, right? So in computer science, in computational complexity, where we study finite objects, we study finite problems up to polynomial time reductions, right? So for example, maybe you know some things about graph isomorphism. The idea there is you would like to have an algorithm that when you plug as an input two graphs via their adjacency matrix, you want in polynomial time the algorithm to stop and say yes or no depending on whether these two graphs are isomorphic, right? So here the problem is finite. In what sense? The moment you feed the two graphs, in the Turing machine, if this graph, the vertex set, has size n, then if there is an isomorphism, you can find it within n factorial tries. There are n factorial time bijections between the vertices. You have to check all of them. So this is a finite thing you have to do, right? So people in computer science study these sort of problems up to polynomial reduction. So if you know how to solve graph isomorphism, which in fact we do not know yet in polynomial time if we can do it, right? But if you know how to do it, you try to reduce it to other problems or reduce other problems to it using polynomial time reductions. So this is about the finite world. Now, when we go to the infinite world, the first thing maybe we want to take a look at is computability. Computability is, again, very similar. It's a complexity theory where you study infinite problems, but countably infinite problems. And here, the right notion of reduction is computable reduction, right? So for example, maybe you care about tilings. And what you want to do is you want to look at the integer lattice. And then I give you a finite amount of prototiles, some tiles that you want to try to tile the entire plane using rotations and translations of these tiles. And you ask whether you can do it. It turns out that there is no Turing machine. This problem is not computable. And in fact, Penrose has contributed in this direction, right? But why I'm saying here countably infinite problems? Because you see, if you give me these prototiles and I'm trying to figure out if I can tile the plane, the attempt to tile the plane, and maybe I'll fail and then I have to start again. If you think a little bit about it, I can go in a spiral. So the amount of searches I need to do is a countably infinite amount of searches, right? So here it's finite. There, the amount of searches I have to do is infinite, but it is countably infinite. So descriptive set theory is a similar type of theory, but it cares about infinite problems which have the size of the continuum. And the right notion of reduction there is the Borel reduction. Right? So let me say a few more words and then switch to things that we care about here. Right? So I just need to give you a couple of terms that will be important for later on. Right? So continuum-sized problems. So how do I think about the continuum? Well, we usually think of the continuum as the reals, but more generally, we would like to be a little bit more flexible. And for me, a continuum would be any Polish space. So a Polish space is a topological space that it is separable, so meaning you can find a dense subset which is countable, right? And it's completely metrizable. So if you want, you can place a metric on it, and this metric is complete. You cannot find Cauchy sequences that do not converge in the space, right? So examples of Polish spaces are the reals, but of course you can take the reals and take countably many copies, right? So later, for example, we may have countably many observables, and we want to place them together in one observable. We can do that and maintain that the range is a Polish space. A separable Hilbert space is a Polish space. The Cantor space is a Polish space. And in Polish spaces, there is a rich and robust theory of definable sets. And for us here, the definable sets will be the Borel sets. Right? So very briefly, so you fix a Polish space, any Polish space you care, let's say the reals, and inside you want to carve out, with simple enough definitions, subsets of it. So the subsets that have nice enough definitions are Borel, right? So for me, a Borel set, the way I think of a Borel set is, if I had a machine that has logic gates of countable length, so countable and, countable or, and negation, and I feed to this machine my topology, all Borel sets can be computed out of this machine, right? So this is what Borel sets are for me. But here's the definition, it's the least sigma algebra that contains the open sets. Now if I have two Polish spaces, we know what a map it means to be continuous, but more generally to be Borel means pre-images of open sets have to be Borel, right? Now, I said before that for me, all these spaces are the same because there is the famous Borel isomorphism theorem that any two uncountable Polish spaces you give me, they are Borel isomorphic. So there is a bijection between them that is Borel. So if my lenses, the lenses I wear and I look at the world with these lenses are the Borel lenses, I cannot distinguish between these spaces. They are the same. And in fact, in set theory, you often say, oh, here is a real. And when you say a real, what you really mean is really an element of a Polish space. This is what a real is in set theory, let's say. All right. So let me go to the previous slide and point out, I said that descriptive set theory cares about continuum-sized problems up to Borel reduction. So what are these continuum-sized problems that look a little bit like that or like that? Well, let's say I give you two Lorentzian metrics, right? So let's say I'm in R4. In R4, my ambient manifold is R4. And here I have the constant Lorentzian metric, the flat Lorentzian metric, right? And here I have some other metric that its entries depend on the coordinates x1, x2, x3, x4, right? And the question is whether these two concrete formulas correspond to the same geometry, to the same physical space-time. And the way we compare metrics is the following. We say that two metrics are diffeomorphic if there is a smooth change of coordinates that pushes one to the other. So this is what do I mean by pushes one to the other. You have to compute the Jacobians here, right? We have seen that, right? For example, here, so this is for me this is a continuum-sized problem that we would like potentially to solve. Why it is continuum-sized? Well, if you have a good guess of what the change of coordinates should be, if some oracle comes and hands you this change of coordinates, then you can easily compute the differentials and plug the formulas and figure out that actually these two spacetimes are the same physical spacetimes. But if you didn't know this witness, if you didn't know this change of coordinates, you had to search in a very big space, in a space that has the size of the continuum. Remember, for finite graphs, you had to search in a finite space. Here, this witness of the fact that these two things are diffeomorphic, this witness is inside the space that has the size of the continuum, and you have to search inside there. All right, so this brings me, so this is the one side of the coin. The other side of the coin is the problem of observables. Right, so here's another way of thinking about these difficulties, the difficulties of deciding whether two spacetimes two formulas about spacetimes represent the same physical spacetime, right? So let's say I have a collection of metrics that I care about. I'll be always denoting this collection by S for spacetimes, right? So there is this collection of metrics, and if I have two metrics, I may ask the question whether they are diffeomorphic. If they are, I will place them in the same orbit under diffeomorphism. By an observable here, I will mean a map from this collection of spacetimes to, well, here this can be the reals, but for me it will be any polyspace. For example, if I have, again, countably many observables, I can put them all together and create one observable out of them. So here I'll be flexible, and this will be any polyspace. So an observable is any map from this collection of spacetimes to a polyspace that is diffeomorphism-invariant. So two metrics are diffeomorphic. This means that they have to take the same value. So we call them observables because these functions should capture physical quantities and not artifacts of the coordinate system. So for example, it could be something like total energy or some other measurement, right? And one of the reasons, in my understanding, that observables were considered was because of their use in quantization recipes, like canonical quantization. So canonical quantization, often the way it operates is first you want to make a complete set of observables. And now complete here would mean enough observables to be able to separate completely non-diffeomorphic spacetimes. So another way of saying that, let's say one observable is complete if you can reverse this implication. If two spacetimes are diffeomorphic, if and only if they take the same values here. Right? So, okay, so in canonical quantization, what you do is you collect a complete set of observables, and then you try to promote them in an algebra of operators in a Hilbert space. Right. So we call it the problem of observables. What is the problem? Well, a little bit of maybe the way at least I've read the history, but there are people here that are more well versed in this topic. So, so going back to Bergman, somehow my understanding is that this is one of the programs that Bergman put forth, right? So here he defines observables exactly in the same way. So functions on the field variables that are invariant with respect to change of coordinates. But almost 10 years later, he remarks here that there are profound technical difficulties in trying to find observables that we can use and do this canonical quantization, implement this canonical quantization program. Right? And these difficulties persist. So for example, in 2001, here there is a quote from Sparling that we can give a formal characterization of observables. This was the previous slide, right? In general relativity, but we actually cannot find explicit examples. We are not able to explicitly construct examples of such quantities. Right? And there is a little bit of a more dramatic take on this later on, that observables for full general relativity without special asymptotic symmetries or matter content almost certainly do not exist. Right? Okay, so me being a set theorist, right, do not exist, it's a very strong qualification. Right? If you allow me to use axiom of choice, and I have the spacetimes with the general covariance here, if I'm allowed to use axiom of choice, I can certainly pick. I can do some gauge fixing here, and I can use this gauge fixing to actually show that observables exist. So what we really mean here is not exist, but whether we can write down a formula that is useful to us. Maybe this is how one should interpret this statement. So this is one thing I want to say. The second thing I want to say is that there is this qualification here without special asymptotic symmetries or matter content. It's a very thing. It's important to realize that if we restrict our spacetimes that we care about, so that they have special asymptotic symmetries or matter content, then you can actually find many observables and sometimes complete observables. So here are some examples. Right? So if you only care about spherically symmetric solutions, then the Komar mass provides a complete observable for the Schwarzschild solutions. And similarly, you can find many observables for asymptotically flat spacetimes. And for when you have coupled metrics with generic dust, then you can also use this dust as a point of reference to develop various observables, right? But the theorem I want to discuss today about is in complete generality, actually you cannot find a way to explicitly define observables in the same way that you cannot construct the cubic root of 2 if I only give you straightedge and compass, right? It's a similar type of theorem. Here's the formal statement, right? So if you give me any collection of spacetimes that contains all vacuum solutions, then I cannot find an observable that it is both definable for me, so Borel, and complete, right? And a vacuum solution is any solution where here I've put the zero as the stress energy tensor. And again, an observable is complete if I have an infinite leaf here. And it's Borel. So here, maybe I have to explain what Borel means, right? So the collection of spacetimes, you can think of them as a subset. It's actually a Polish subset of all smooth maps from R4 to R4 times 4. For every point in R4, you need to choose a 4x4 matrix, right? This is what this is, right? And here you can place a topology, which is known as the C-infinity compact open topology, which makes this a polyspace. I can discuss later if you want what this topology is. But if you are suspicious about this topology, there is a way to restate this theorem without any mention of the topology. Here is how to restate it. It's a little bit more technical, but think of it this way. If I allow you to use the usual axioms of set theory, but I do not give you access to axiom of choice, so you cannot do this gauge fixing. So I do not give you access to axiom of choice. So ZF is all axioms of set theory without choice. DC is I give you back a little bit of choice. And here the idea is that you cannot even do analysis. You cannot do analysis if you don't have a little bit of choice. Like to prove that a countable union of countable sets is countable, you really need a little bit of choice. So to be able to work with sequences that converge, you really need some choice. The amount of choice you need is dependent choice is more than enough, right? So if I give you all axioms of set theory without choice, and I give you back a little bit of choice, not full, but enough to do analysis, still it is consistent that there is a set theoretic universe that satisfies these two things, but also in this universe, there is no complete observables for this collection of spacetimes whatsoever, right? So without no qualification about definability, just you cannot build it. There doesn't even exist in this universe, right? All right, so I say I'm running a little bit on time, so how much time I have?
You have another 12 minutes.
Okay, perfect. Right, so let me then discuss very briefly some ideas from the proof of this. Right, so the idea goes back to ergodic theory. And the way ergodic theory has been used in representation theory. So the tools we're using for that essentially go back to the 60s. So it's difficult to understand general covariance in this context. So maybe what would be easier to do is to change a little bit and study first a problem that maybe is simpler, right? And the problem that is simpler is the following. So you look at the space. These are all bi-infinite sequences of zeros and ones. So here's how an element in this space looks like. So for its integer entry, you have to place either a 0 or a 1. And you declare two such sequences equivalent if you can shift one, and then you have equality point-wise, right? So they are equal up to a shift, right? So instead of looking at the spacetimes up to diffeomorphism, I'll be looking at this up to shift. Now, here's an old theorem coming from measure theory. So in this space, you can put the coin flip measure, a probability measure, right? You place 0 or 1 here with probability 1/2. It turns out that this measure is shift invariant. And now there's a theorem here that if you give me a Borel map to the reals, but here you can place any polyspace, right? If you give me a Borel map, if this map is invariant, so it's like an observable, think of it, right? Then in this space you will find a probability measure 1 set on which the function is entirely constant. So basically, any reasonably definable observable, it's essentially constant almost everywhere. You cannot really distinguish between a lot of different orbits here. Many different orbits will collapse to a singleton, right? So this tells you that it's a very strong way of saying that even on this context, you do not have complete observables which are Borel, right? So once you know this theorem, the idea is how to try to reduce this here. So here's the general strategy for. So basically, the idea now is that I have a hammer, and I'm trying to find nails, right? And how do I find nails? I know that this is a pathological situation here. I mean, maybe a picture here is worth drawing, right? The way you have this pathology here is that in pictures, we often think of orbits like that. But here, if you think a little bit about how orbits look like, they are dense inside there. So they look something like. So if you give me two orbits, they are so highly tangled with each other that it's very difficult to separate them, right? So now the idea is, the moment you know that, to try to reduce that there, using what we call a Borel reduction, right? So if you give me a collection of spacetimes where I can reduce this inside there, so reduction means a map that takes points from here to points here, and 2 points here are in the same orbit, if and only if their images are in the same orbit, right? So this is what I want to do. So if I have such a Borel reduction, then I cannot find complete observables here, because if I found complete observables, Borel complete observables here, by precomposing with this reduction, I would have found complete observables here, contradicting this folklore theorem, right? So now I have this hammer, and I'm trying to find nails. You can try to apply it to various collections of spacetimes, right? So here is like a toy example. Like if you don't care about how simple your stress and energy tensor coupled with a metric is, there are simple constructions you can do, right? So basically, you can take this family of Friedman, Lemaitre, Robertson, Walker metrics, and use this function here to code these zeros and ones by putting bumps, right? And this allows you to build a reduction from here there. Now, I don't find this very satisfying, and I say this, it's a toy example, because here I do not have basically the complexity of these bumps is already coded in the stress energy tensor. So basically here I'm not fixing the stress energy tensor, I'm varying this as well. So a more difficult and more interesting question is if you can fix the stress energy tensor, look at the solutions with this fixed stress energy tensor, and if you can do a similar trick. And it turns out that even in the simplest case, when we work with vacuum solutions, where the stress energy tensor has been fixed to 0, if you are in dimension 4, then you can still reduce this Bernoulli shift there. Mind you, that if you work in 3 dimensions, you cannot do that because there is essentially only one geodesically complete vacuum spacetime. Right. OK, so this takes some work to prove how to reduce this there. The idea is to go through plane waves. So basically, the plane waves, you look at the spacetimes that look like that, where you have a function, a smooth function of u, x, and y that satisfies this differential equation. If it satisfies this PDE, then it's a vacuum solution. And now you're trying to experiment with functions like that. And if you play a little bit around, you can shoot the Bernoulli shift inside the collection of all plane waves. Right? So you can create this reduction, and then you have to show that indeed it's a reduction. And there are 2 steps here. One step is easy, the other is hard. And maybe the only thing I want to say here is really, what do I mean by the one direction is hard? If you try to do it, bare hands, it's very difficult. You have to solve something very difficult. But instead, what you can do is you can exploit the symmetries of the metrics of the plane waves. And this is what we do to prove that this is indeed a Borel reduction. So if I have 3-4 more minutes, maybe I want to say a few more words about future directions. So it seems to me that some of these ideas coming from descriptive set theory, but also from the problem of observables, sort of point in the direction that there should be some uniform program here, research program, right? Maybe, let me call it a descriptive cage theory, right? So here's the idea, the premise. So we discussed about how complete sets of observables are useful for canonical quantization. What we showed is that in general, in complete generality, you cannot have them. But maybe the observation here is that if you still want to save this, or you want to pursue this specific way of trying to quantize gravity, I'm not saying this is the right way to do it. I'm just saying if you want to pursue this direction, a useful observation here is that your end goal is an algebra of operators. An algebra of operators live in a Hilbert space, and the same way that the metric lives on a manifold, and the manifold has the ambient symmetries of diffeomorphism, the algebra lives in the Hilbert space. The Hilbert space has its own symmetries, the unitary group. So maybe what you want to do here, what you want to experiment with, is what I would call equivariant forms of quantization, where you want to map metrics into various other gauges which have nice representation theoretic properties. Right? So maybe you want so something like that. So you have a G mu here. You want to associate to this some, I don't know, something like this. And if I have another, let's say, G tilde rho sigma to map it, something like that. And maybe you want these two things to be diffeomorphic if and only if these two things are unitarily equivalent using some restricted amount of unitaries that come maybe from the unitaries of a sister algebra. I don't know. Maybe you have, right? So the point here is that maybe try to connect this up to some gauge, right? So modern invariant descriptive set theory gives you a toolbox for deciding whether these things can be done in a definable way. So there is a whole complexity zoo here in descriptive set theory. It's called the Borel reduction hierarchy. Points in this complexity zoo are pairs like that. X is a polyspace, is an equivalence relation. Think of it as a gauge. And you can compare these gauges using Borel reductions, whatever this is. And maybe the program, and I'll leave you with that, would be something like try to place spacetimes up to diffeomorphism or spacetimes up to conformal isometry, depending on what you care about. And spacetimes you can choose. Maybe you want all of them. Maybe you want vacuum solutions. Maybe you care only about asymptotically flat metrics. And try to figure out where this fits inside this complexity hierarchy. And this complexity, let me just draw a couple of complexity classes and I finish. So down here is reals or a polyspace up to equality. And it turns out that if the group G that acts on a polyspace, if G is compact, then the gauge cannot be above. It has to be very, very simple. This is the simplest it gets. Here is the Bernoulli shift of the integers. What we did is we showed that this doesn't reduce here, so it has to be higher up. But where do we want to place it? This is the complexity class when the group is locally compact. So locally compact groups can have more complicated gauges. And the next step is to try to see if you can squeeze if the complexity of this can be if this gauge, the diffeomorphism gauge, can be reduced to the gauge of a locally compact group. Somewhere here are unitaries of separable sister algebras. This is the gauge. These groups can produce bounded complexity gauges, and there is a very, very big open problem in this area. Question: if the dynamics of the unitary group, of the general unitary group, bound the complexity of the gauge, right? We don't know. It is likely, it's possible that every orbit equivalence relation, maybe it's reduced for some abstract reason to a gauge of the unitary group. It's an open problem. It's likely that the answer is no, meaning that there are things that are more wild in dynamics, more wild gauges, than any gauge that the unitary group can produce. If that's the case, then this may give an exciting opportunity that maybe the gauge of the diffeomorphism group cannot be reduced to any action of the unitary group. Maybe it's higher up here. And this maybe will give some obstacle to implementing canonical quantization even in an invariant way. All right, so I'll stop here. Thanks.